All right, we're going to start this lesson by just going over some simple stuff regarding the radian for each degrees. 0 degrees is going to be 0 radians. 90 degrees is 1/4 of the way around our circle, so 1/4 of 2 pi is going to be pi over 2 radians. 180 is halfway around the circle. There are 2 pi radians in a full revolution, so half a revolution there is going to be pi. 270 is 3/2 pi, or 3 pi over 2, and 360 is 2 pi. You can do the thing where you take your degrees and multiply it, put it over 1, and then multiply it by pi over 180. For every 1 pi, you travel 180 degrees, and when you do that, you'll see, for example, that would become pi over 2. So today we're going to talk about graphing trig functions. We're going to graph sine and cosine curves. We're going to understand period and amplitude using shifts of A, H, and K. We're going to focus primarily on our amplitude today, which is going to be A. So this is a unit circle here, and we're going to label our ordered pairs, and we're going to talk a little bit more about this unit circle. Okay, this first point here is going to be 1, 0. That's also at 0 radians. Up here, we're going to have 0, -1. Again, we don't move, 0, +1. I don't know why I put the negative on that. And that's also located at pi halves radians. Over here, this is going to be the exact opposite of here. So this is -1, 0. 0, -1. Right here, we've traveled halfway around the circle, so we're at pi radians. Here we've traveled 3/4 of the way around, so that's 3/2 pi. And finally, over here, we're at 2 pi radians when we finish completely. Something that's interesting to note, if I take the sine of 0 degrees, that's going to be equal to 0, because there's really no opposite side. If I try to take a triangle and draw a triangle there, there's no opposite side. Cosine of 0 is equal to 1. If I look at the sine of 90 degrees, or pi over 2, I put that in my calculator in radian mode, I get 1. The cosine of pi over 2 is equal to 0. I can do the same for the sine of pi. The sine of pi is equal to 0. The cosine of pi is equal to -1. I can do the same for the sine of 3 pi over 2. That's equal to -1. And cosine of 3 pi over 2 is equal to 0. If you start looking at it, one thing you'll notice is that our ordered pairs here correspond to this: cosine of theta and sine of theta. Such that as long as we're on the unit circle, and I think we've mentioned this before, as long as I'm on the unit circle, my coordinates along the unit circle always respond to the value of cosine for x and sine for y. It's also important to think about this because these values are going to play a role into how we graph sine and cosine functions. But again, remember, cosine of theta is your x-coordinate and sine of theta is your y-coordinate. Keeping this in mind, we're now going to take the function y equals sine of x and we're going to put it on an xy graph. Now it's important to remember that, again, all these values here and here and here and here correspond to cosine of theta and sine of theta. Also to remember that at 1, 0, we're at 0 radians. 0, 1, we're at pi over 2 radians. At -1, 0, we're at pi radians. And at 0, -1, we're at 3/2 pi. So I can come up and say that sine of 0 is equal to 0. By that same token, I can say that sine of pi over 2 is equal to 1. Sine of pi is also equal to 0. Sine of 3/2 pi is equal to -1. And finally, sine of 2 pi is the same as sine of 0, which is equal to 0. Now, if we look at our graph that I have labeled here, I have used on the x-coordinates our angular measurements: pi halves, pi, 3/2 pi, and 2 pi. And I can start graphing this. When my input is 0, for sine of 0, my output is also 0. So that would be a ordered pair of 0, 0. I can put a point there. When I have sine of pi, or sine of pi halves, that's equal to 1. My input is pi halves. My output is 1. So I can now put a coordinate or a point at pi over 2, 1. Again, I can do the same here. When my input is pi, my output is 0. Put an ordered pair at pi 0. For here, I would have 3/2 pi, -1. So find a point at 3/2 pi, -1. And finally, I would have 2 pi, 0, which would be right here. And now when I graph, I'm going to connect the dots. And I'm going to curve them. And this, while not perfect, is what a sine curve looks like. In fact, I'm going to clean that up a little bit. And that's a sine curve. And so what we've done is we've taken our trigonometric function from the unit circle and now put it on an xy axis. All right, so as we did for the last slide when we were looking at y equals sine of x, I'm going to go through, and not only do we have the coordinate points, the ordered pairs labeled for each of these points on the unit circle, I'm going to remind us of our angular measurements. That's 0 radians, that's pi over 2 radians, that's pi radians, 3 pi over 2 radians, and again, when we come all the way back there, that is also 2 pi as well. We noticed here for our x-axis are all of our angular measurements: pi half, or 0, pi halves, pi, 3/2 pi, and 2 pi. Our y-axis is just our y-coordinates that are along the unit circle. So if I remember correctly, I can look at cosine of 0. When I think of cosine, that's adjacent over hypotenuse. If I think about a triangle, a 0-degree angle, and drawing a triangle there, my hypotenuse and my side adjacent are essentially the same side. They're both going to measure 1, so my cosine of 0 is equal to 1. Notice how that's also my x-coordinate. Cosine of pi halves is equal to the x-coordinate, which is 0. Cosine of pi is equal to 1 as well, or -1 in this case. Cosine of 3/2 pi is just equal to our x-coordinate, which is 0. And cosine of 2 pi is the same as cosine of 0. It's going to be equal to 1. So I can go through now and graph these as ordered pairs. I'm going to write the ordered pairs out just for our convenience. So we're going to have 0, 1 here. We're going to have pi halves 0, if you can see that. -1, 0. 3 halves pi 0, and 2 pi, 1. And I'm going to go, like I said, I'm going to go ahead and graph these. 0, 1 is going to be up here on the y-axis. I'm going to then hit the x-axis at pi halves 0. I'm going to go down below there to -1, or sorry, that should be pi -1, my bad. At pi -1. I'm going to graph at 3/2 pi 0 and at 2 pi 1. When I connect the dots here, I notice that it looks a little bit different than a sine curve. This maybe looks like the valley between two peaks. where if you remember our sine curve looked more like a peak followed by a valley. And that's part of the difference between sine and cosine. I think you could say they're out of phase by pi over 2 radians or 90 degrees. A few definitions here. A period is how often the graph repeats itself. A regular period is 2 pi. So if you think about it, and we'll draw this out, a sine curve looks like this, and it starts by going up, then by going down, then by coming back to the x-axis. Once it starts going here, it starts repeating itself. And this, of course, is at 2 pi. The midline is halfway between the highest crest and the lowest trough. So if we were to talk about a curve and it would look like this, our midline would be right here. That would be the midline. I'm going to highlight that. It's halfway in between here and here. And our amplitude then is the distance from the midline to the crest or trough. So again, if I have this being my x-axis here, and let's say I look at a cosine curve, what I'm going to draw in blue is my amplitude. That goes from the midline to the crest here, or from the midline to the trough. And that is my amplitude. A full sine and cosine function are given by y equals a times sine of bx minus h plus k, and y equals a times cosine of bx minus h plus k. As we've been familiar with already, for a in functions, that is our amplitude. It tells us a vertical stretch, shrink, or reflect. And as we look at our next slide, you're going to see how that will affect how far above the midline and how far below the midline our functions will go. Again, we're simply going to take our values that we've already established for sine and cosine, and we're going to multiply them by that amplitude. So all those times when we came up with a 1 as an output, it's going to be now whatever the value of a is. And of course, obviously, if our output was 0, that's not going to affect everything. So basically, our x-intercepts are going to remain the same, but our y values will change. I'm not going to go ahead and rewrite all of our measurements or angular measurements around the unit circle above, but I'm going to start by saying that we remember that sine of 0 is equal to 0. We remember that sine of pi halves is equal to 1. We remember that sine of pi is equal to 0 again. Sine of 3 halves pi is equal to negative 1. And I'm going to skip sine of 2 pi because we know it's the same as sine of 0. Now looking at the function I do have, I see that my amplitude is 3. But I already know the values down below for sine of x for all those values of 0, pi halves radian, 0, pi radians, and 3 halves pi radians. So I can now say that when I have 3 times the sine of 0, that's just equal to 3 times 0, which is still equal to 0. That's an ordered pair, so I still have the ordered pair 3, 0. If I take 3 times the sine of pi halves, that's just equal to 3 times the sine of pi over 2, which is 1, which is going to be equal to 3. So now my ordered pair there is pi halves 3. If we think about sine of pi equal to 0, if I multiply that by 3, no change. So therefore, let's look at the more interesting case of 3 times sine of 3 halves pi. Well, we know that's just going to be equal to 3, which is our amplitude, times sine of pi half, or 3 halves pi, which is negative 1, and 3 times negative 1 is equal to negative 3. So I'd have the ordered pair there, 3 halves pi, negative 3. And I can graph these ordered pairs plus the other ones that I know of very easily. So again, my sine wave or my sine function starts out at the point 0, 0. got that one. It's going to end at 2 pi 0, so I can draw that point in as well. At pi over 2, my output is 3, so notice what I'm going to do here. I'm going to label my y-axis 1, 2, and 3, and I'm going to label the point pi halves 3. At pi, I know that I have an x-intercept, so at pi, my input is 0, whether it's at 0, 3, or whatever. And now, again, at 3 halves pi, my output is -3, so I'm going to go down 1, 2, and 3. And I'm going to put a point at 3 halves pi, -3. I can connect the dots then, and again, it looks exactly like my sine curve did, except for one difference. I now have an amplitude of 3. And that is the only difference. I still maintain all of my x-intercepts here, here, and here. And my peak is still at pi halves. My valley is still at 3 halves pi. And again, only thing that changed is my amplitude went from being 1 to 3. All right, for our next example here, our amplitude is -3, which means our amplitude is equal to 3. So we'll go 3 above and 3 below our midline. But this negative sign gives us a reflection. Again, something we're used to. So I already know that my amplitude is going to be 3 above and 3 below. So I'm going to draw those in. In my previous graphs, I've started at 0, 0, and I've gone to pi halves, and I've gone up. But this time, my reflection is going to have me at pi halves have a negative value, and in this case, -3. I'm still going to have the same x-intercept, so I'll be at pi 0 and at 2 pi 0. The only other difference now is 3 halves pi, usually used to dealing with a negative number, but since I'm doing a reflection, it's now at +3. So now my curve, my sine curve, starts beneath the x-axis and finishes going above and then coming back on the x-axis from the top. As we see now, our amplitude is still 2, or still 3, from the midline up, but since we start downward, that is where the -3 comes from. All right, so now we're going to take a look at cosine. Just as a quick reminder, our cosine of 0 was equal to 1. Cosine of pi over 2 is equal to 0. Cosine of pi was equal to -1. Cosine of 3 halves pi was equal to 0. And of course, cosine of 2 pi was equal to 1. If we notice now that our amplitude here is 4, all those values are just going to get multiplied by 4. So now 4 cosine of 0 is equal to 4. 4 cosine of pi halves is still equal to 0. 4 cosine of pi is -4. Cosine of 3 halves pi is 0, so multiply by 4, it's still going to be 0. And 4 cosine of 2 pi is 4. That gives us an amplitude of 4. We could have skipped all that by just marking off 4. 1, 2, 3, and 4. And also -1, -2, -3, -4. Cosine starts at 0, 4 in this case. So we'll put a point there. Again, it starts at our y-intercept. Our first x-intercept is at pi halves. That's going to remain the same. Our second x-intercept is at 3 halves pi. At pi, we are going to be at -4 now, as opposed to -1. And at 2 pi, we will end up back at +4. We connect the dots here. We see our valley shaped in the middle with the 2 peaks on the end. and we see that our amplitude here is 4. See an amplitude of 4 here, and an amplitude of 4 here. We see the vertical stretching that has occurred. If we were to look at the original cosine function, we'd start off here, still going through the same x-intercepts. Still going through the same x-intercepts, but here our amplitude would only be 1, 1, and 1, and we notice that it's going to be a vertical stretch of 4 times as tall or 4 times as deep. Now, if we're able to construct a sine and cosine curve from the function, we should be able to go back and look at the graph and determine whether or not we have a sine or cosine function and build the function from the graph. So let's start off. The first thing we have to do is figure out whether this is a cosine or sine function. And the biggest key is going to be that we start at the point 0, 0. When we start at 0, 0, we need our function to have an input of 0 and an output of 0. Well, let's go back over here. We know that cosine of theta, sine of theta is our x and y values. So we're looking at here an x value and a y value of 0, 0, which means for 0 radians, we need our y value to be 0. And the only way that's going to happen is with our sine curve. We see that sine is 0. We see that our input of 0 radians is 0. So this has to be the sine curve. Let me try to clarify that again. Sine functions are always going to start at the midpoint, or the midline, I should say, of our trigonometric function. So we know this is sine. So now I can start by writing that y is equal to a sine of theta, or x if I want to do that. I guess that might even be more appropriate here. Now all I have to do is figure out what my amplitude is. And I can look here and I see that this is my midline, my x-axis. So how far above the midline do I go? Well, I go to above it, I go to below it. And I start out by traveling in a positive direction. So my amplitude here is equal to 2. Since I'm going in a positive direction, I have y is equal to 2 sine of x. Now let's look at this other equation. Again, our goal is to build the function back from the graph of the function. Looking at it, a couple things. We're going to look at our starting point. Our starting point is at 0, negative 4. That's where we're starting at. Okay, a couple things to note. We're not starting at the midline. If I look, the midline appears to be, again, along the x-axis. Since I'm not starting at the midline, I have a cosine function. Okay. The other thing to notice is that I'm also starting at the negative 4. I'm starting below the x-axis. Our cosine curves typically start above the x-axis. So that tells me there is a reflection, which means I'm going to have a negative a value. Now I just have to figure out my amplitude. I already know the function is going to be some kind of cosine function. I know I have a negative value here. And so now all I have to do is figure out how big my amplitude is. Well, this is the midline. I'm going up 4. I also went down 4. So I have y is negative 4 cosine of x. All right, that is our lesson on amplitude. I hope that makes a lot of sense. We'll have another lesson tomorrow. Go ahead and get started on your 11.1 worksheet. And please remember that math puns are the first sign of madness. See you tomorrow in class.